joined the GTC staff to work with Emir. So Emir is his main kid, child these days. Okay, but he also has a number of science topics he works on closely related to the Milky Way or the local group. And today he's going to tell us something about a very recent discovery of a nova in M31.
So first, just to clarify that this is not my primary science topic, but as I mentioned to Jesus earlier, I think that when person is giving a talk, it's better to kind of push its own limits as well. So now I'm presenting a project that we've been advancing during the past 3 or 4 months, and it is related to a luminous red nova that appeared in the Andromeda galaxy. And down here you could see the different designations that the object got over the time. Overall, a short outline of the talk. First I'll talk a little bit about the detection and discovery of the transient. Then I'm going to present the follow-up photometry that our group did. Then I'm going to move to spectroscopy, something that is very interesting in particular and important in this case were the extinction estimates for the object. Then we have some estimates for the parameters of the system, short overview of the field, let's put it this way, what we do for the ongoing observations, and of course future work. First of all, the detection and discovery, it is a very interesting topic because this particular transient in Andromeda was discovered by a fully automated system that is operated mainly in Russia. But they also have telescopes in the southern hemisphere, in South African Observatory, and also in Argentina. And generally the auto detection system picked up the transient on 13th of January and automatically derived the initial coordinates, and of course it got the designation that was related to this particular auto detection system. Here you could see generally the discovery images, also compared to a comparison image that was taken in December the previous year, and generally both images are with a magnitude limit of 19.6, and the transient at that time was of a magnitude about 19. So that was an optical transient that was discovered very early during the evolution of the object. And a little bit about the system that was used for the discovery. MASTER goes for Mobile Astronomical System of Telescope Robots, and currently there are 7 observing sites that are operational. 5 of them are located in Russia, and as I said, there are 2 international sites. And every site is equipped actually with 240 centimeter telescopes, mostly for detailed follow-up, and then it has 2 very wide field cameras that generally have a shower limit, but they are used, for example, for discovery of brighter objects. And of course, like many of those systems that are operational nowadays, it is geared towards fast observations of gamma ray bursts, supernovae, novae, and generally all kinds of transients, fast transients and not so fast, like for example minor planets, comets, asteroids, everything that could be of interest. And down there is actually the paper that is giving a more detailed overview of the entire system. Generally, once the transient was discovered, actually I was contacted by a friend and colleague of mine from Bulgaria, and generally there are several Bulgarians all over the world that we kind of started that collaboration, but then it grew up significantly. You'll see towards the end of the talk. And for the follow-up, it turned out that we basically used 8 different telescopes that range from half a meter to a 6-meter aperture. And it is generally really worldwide, 3 continents, 7 observatories. And for the purpose of getting observations in a more homogeneous scale, we decided to go for the Johnson's cousin sets of filters, because it turned out that those were the filters commonly available in all of the observing sites that we had access to. And because you could imagine that this could involve a lot of systematics, the decision was taken to generally calibrate 4 nearby stars next to the transient that have a span in colors and magnitudes to use them as internal standards in the field in order to get a reliable photometry from the different data sources. And generally those stars were calibrated using the catalog of Massian collaborators from 2006, or basically this is part of the series of works that were done on the local group survey. Generally in this particular talk I will present mostly the initial period of monitoring from early January to late March 2015, and generally we got more than 70 different data points, and there are a number of astronomical telegrams that basically list the preliminary or the results as they were at the time. What you could see here is generally the evolution of the light curve of the object in BV, R and I think that it is easy to see the color coding, and also it is presented the evolution of the colors of the object. Generally everything is presented in days since 22nd of January, which was the estimated time of the peak brightness of the transient. As you could see, generally we have quite a rapid initial increase of the brightness of the object. The colors are getting bluer, but then generally it phase of decline initiates, and it is something which is typical for those luminous red novae. The decline is much more rapid in the blue part of the spectrum, and generally, as you could see, the colors that involve the blue filters are really getting to a red values really quickly. And generally, what you could see here are everything that was observed until the first day of April 2015. And overall, which is kind of interesting, here at the Canary Islands, we used Nordic Optical Telescope to get several data points, particularly towards the end of the period when Andromeda was setting really fast at the beginning of the night, because NOT has the advantage of being able to point really low at the horizon. So that gave us the opportunity to secure several more photometry data points. 6 degrees above the horizon. If they open the lower hatch, which there are some limitations related to the wind that is persisting at the time, but if the lower hatch is open, it could go as low as 6 degrees above the horizon. And actually, we utilized that for some of those observations in order to be able to get the photometry of the object. So basically, these are the results of our group, but I also tried to outline some results from other people that were published. Generally, there is an astronomy telegram that is dealing with the identification of the progenitor system. Overall, I also did a search in the HST archive, and by chance there were a couple of images. One image which is F814W, which is analog of the I band that we know for the ground-based photometry. And there is also another image which is in V band, and also one of the white filters that generally had imaged the same field in 2004. And also this group reports photometry on their own proprietary images from CFHT, which could turn very interesting because I've also had a look at the data set. Generally, they have been observing that part of Andromeda with CFHT for microlensing events. So they were accumulating data nights in a row on the same field, and the object is in there. So the persisting theory for the occurrence of these transients is that basically it's a stellar merger event. And in the light of that theory, if you have such a long photometry data series, it's possible first to see how the luminosity of the system varied over time, and potentially it's possible also to detect changes in the period of the system, which is related to the loss of orbital momentum. So generally from these observations, I think that there could be very interesting results in the future, but the data is proprietary. It was observed just in October 2014, right before actually the transient occurred, and that makes actually the data set really, really valuable and interesting. We also did spectroscopic observations, and here also we have quite a heterogeneous set of observing facilities, ranging from the 2-meter telescope at the Bulgarian National Observatory, and generally we also were lucky to be awarded director discretionary time at Grand Tecan. And in half an hour we managed to observe a spectrum of the object using the R2500 B, V, and I grisms. So we have a pretty large chunk of the optical spectrum that is covered. And generally, at the end, in order to get the data in a little bit more homogeneous way, these are the data, the parts of the spectrum that we've been studying, and they come from different observatories. Generally, what is marked in red comes from the 6-meter telescope in Russia. In green is from the observatory in Bulgaria, and we have one observation on February 24th that comes from GTC and Osiris. So first of all, the spectra from Bulgaria, they were acquired with relatively small telescope, and they were acquired also early after the discovery of the object, so we could see some kind of evolution, but also the object is a little bit faint for the telescope. Also, the instrument that was used is called FORERO, or focal reducer Rosen, which was done mostly for cometary work. It turned out that when I was starting my career, I was supporting for a few months the instrument, and generally it's really like a Swiss Army knife. You could do many things with the instrument, but it's really hands-on and it requires a lot of effort. So the first spectrum that you could see up there is actually observed on January 14th, or one day after the occurrence of the optical transient. And the only thing that you could see after really massive binning of the data, it is binned to 16 angstroms resolution, is that you could see some hint of H-alpha emission. And that was actually the first reason why the transient was cataloged as a classical nova because the H-alpha emission is something that you expect to see. The second spectrum is observed with the same instrument, but now the H-alpha emission you could see is much stronger. It is actually observed 2 days later on January 16th, and generally the intensity of the H-alpha had increased enormously, and generally over the same period of time the part of the group that works at the Russian observatory, they reported also observations of H-beta on their spectra. So up to that point, the transient was evolving a little bit brighter than we would expect, but it had all the features that are expected to be observed in a classical nova. That was generally the time we decided to apply for some DDT time at GTC, more with the aim to obtain a homogeneous data set of monitoring the spectra of the object over time with, let's say, 1 week of temporal resolution. But at that time, I really honestly think that the proposal wasn't really strong enough. So generally first the committee was really nice and contacted us and said, okay, if you are willing to use, for example, William Herschel, which we tried to do, but unfortunately due to the combination of weather and technical issues, we couldn't observe the object initially, and then generally we were awarded half an hour at the GTC, which was right at the edge of the visibility of Andromeda for that facility, and we managed to acquire a spectrum. So moving further, here you could see the 3 spectra that we have from the Russian 6-meter telescope. So just to mention, the spectra that you saw on the previous slide were acquired with 1 hour time on source, and you see that short of the H-alpha emission you cannot see almost anything else. These are the spectra from the Russian telescope, more or less with the same exposure time. And the interesting thing here is that generally all the spectra are normalized to the spectrum of January 21st. It is kind of normalized to unity because that is the spectrum obtained closer to the peak luminosity of the event. And first you could see that the early spectra on January 15th, they are mostly featureless. Then we have the change of the intensity and also the shape of the spectrum that roughly corresponds to the change of the optical colors that were observed. And finally, in the spectrum of 21st of February, you could see that generally first the object is getting much less luminous, and also at this point you could start really seeing some stellar-like features in the spectrum of the object. Just a second, we could just go back to, oops. Yeah, that's in the opposite direction, I'm sorry. Okay, so the difference, V minus R maybe is a good indication in that respect. So here we have about 0.3. And that is close to maximum light, and here it is a little bit redder. Here, 1 month further, it is. Yeah. Yeah. I think that, yeah, half a magnitude is accurate estimate. And finally, going to the GTC spectra. So basically, the spectra before, they're also kind of with an exposure time close to an hour with a 6-meter telescope. For the GTC spectra, we wanted to get as much as possible in the time that we had. So generally, the spectrum is in the middle, the black line, and sorry, it's February 24th. It is not January. Generally, this spectrum is obtained with exposure time of 6 minutes on source for each of the grating settings. So it is with significantly less amount of time. And overall, you could see that right now we are starting to see many features that are typical for the stellar spectra for cool stars. For example, here we have the titanium oxide bands, and what is shown here is a comparison with 2 supergiant stars, just to from a stellar library, just to see to get an idea about the stellar parameters that are corresponding to the system. Something that is not seen very well here, if you kind of squint your eyes, you could notice it, is that there is also a little bit of H-alpha emission. And the interesting thing about the H-alpha emission is that it is generally double-peaked profile with a kind of central absorption feature. I'm not sure if this is really 2 H-alpha lines that are, one is a little bit blue-shifted, the other one is red-shifted, or we really see H-alpha in emission and some kind of absorption overimposed, and this is something that we're still discussing how to generally interpret that observation. So H beta emission, it disappeared really quickly after it was observed around the moment of maximum white, and that was really interesting. Unfortunately, from the Balmer series, all the data that we have, we could just see H alpha and H beta. H beta disappeared first, and then H alpha you could still see some emission, but it is really weak. And actually, from some of the estimates that were made in January, close to maximum white, it is clearly visible because there were data taken in H-alpha filter and in broad band R filter. Actually, almost all the emission that the object had in R band is due to the H-alpha emission of the transient. So, but there is also photometry that was reported in by other groups, and generally I'm just listing the telegrams that were published. The interesting part is that for now all the groups that are working on the object basically agree on the stellar features that are observed in the atmosphere of the of the transient, and also the other interesting thing is that generally the estimates of the expansion velocity are in a good agreement, taking into account the systematics between the different observations. So something else that we spent quite a lot of time working on is actually getting an accurate extinction estimate for the position of the transient, because like it usually happens when an interesting object appears, it is out of the fields that were observed with the direct project during the 90s. That was a project to observe Cepheids in the Andromeda and get direct estimate for the distance to the galaxy. It is also out of the fields that were observed as part of the panchromatic Andromeda HST survey, and generally the only way to get some information about the extinction, accurate information, is actually to fit the spectra that we had, and we use the GTC spectra because they have the broader wavelength coverage. With the fit spec procedure from the STS-DAS package, using stellar templates, and by that trying to get the estimate of the extinction. So generally that was done for all the spectra that we have from the Russian data set, and also the data from the GTC, and at the end we agreed on the average extinction estimate of 0.45 magnitudes plus minus 0.1 magnitude. So that is important generally to get an idea about the, for example, luminosity of the object. So overall, if you just look at what most people that are doing extragalactic astronomy are using, these are the extinction maps of Schlegel, for example, or now there is a new reincarnation and recalibration of the extinction maps, and that's the work of Schwaffi and Finkbeiner, 2011. That is using the same Kobe-Dirbe data sets, but they're just deriving new calibrations. Generally, they are also prone to the same, how to say, weakness, because in the direction of Andromeda and also the Magellanic clouds, there is just overall estimate of the foreground extinction in the Milky Way. You cannot really get an extinction for a point in the Magellanic clouds or Andromeda, and that is because, as far as I know, the instrument that they were using, the data set is basically saturated in these directions. Also, we did a quick check using the using the catalogs published by Worthy and Lee. These are generally stellar covers, and using the covers that we were measuring on the image. And overall, for comparing with their published values with what we have measured, gives a reddening that is variable in the point of 0.15 to 0.58 magnitudes. Overall, that shows that the estimate is consistent. Basically, the value that we have, one part of it is due to the foreground galactic extinction, the other is attributed to Andromeda itself, and using that estimate, and also the distance to Andromeda, standard extinction wall, and the corresponding volumetric correction for the B minus V color that we calculated for the moment of maximum light of the transient, we get the estimate that it had an absolute magnitude of minus 10.4 plus minus 0.3, or a luminosity of about 1.2 10 to the 6th solar luminosities. Generally, if you compare that within the error bars, for example, that is within the estimates for V838 Monocerotis that were done by Howard Bond and Bill Sparks at the Space Telescope, based on the measurements of the light echo around that object. So generally, that is one of the results that reinforce that basically we are observing luminous red nova in M31. So no, I think that it is not how it's called, the survey, panchromatic Andromeda HST survey PH. Yes, I'm talking about the. Basically, it is within the MASI survey. Probably it is within the PANDA survey, but generally, if you want, for example, to estimate the extinction, of course, with the resolution and the broad wavelength coverage that the HST survey is giving, it gives you much better handle. Yeah. So that is short overview where we are standing in the field overall. First, in the recent years, there were works published that the first actually observed nova, CK Vulpicua, was that kind of optical transient or a luminous red nova. And interestingly enough, almost nothing happened in that field until the end of the 80s of the previous century. Generally, in 1988, Michael Rich and collaborators, they discovered similar transient again in Andromeda, and it was designated M31 LRN. And then there were similar transients discovered in our galaxy. Of course, the object in Monosrotis being the most, how to say, the one that is studied in great detail, and it is also well known. But before that, in '98, there was transient in Sagittarius, and the most recent one, again in our galaxy, which is from 2008, is V1309 Scorpius. The interesting part about the light curve that we have is that if you look into it, it does not compare at all to the light curve of V838 Monocerotis. It is very interesting because in the Monocerotis event there are actually 3 consecutive maxima, which we don't observe here, but also comparing with the light curve of the event in Scorpius from 2008, they are almost identical. And this is actually another interesting point. It may turn out that actually the family of that luminous red nova is much more rich in properties than we could expect based on the relatively small number of events that have been observed up to date. And that basically makes any follow-up observations and accumulation of data really interesting. And in that respect, generally, we are still trying to follow up this event. Generally, the most recent result is actually from the 5th of May, shortly after Andromeda appeared again with the Nordic Optical Telescope, using the ability to point really low. We got E, R, and B images, but those were acquired at the end of the night and the morning twilight. So generally, the sky background is increasing really quickly. So the only thing that we were able to get is a reliable estimate for the eye magnitude of the object, which is 20.9, almost 21st magnitude right now. And for the R band, we have kind of a lower limit of the expected magnitude. Generally, right now, the object is getting into magnitudes that are really into the realm of bigger aperture telescopes, in terms of, especially if you want to do monitoring in the spectral monitoring. And if I just go really quickly to illustrate, for the I-band magnitude, the last observation that we have is, let's say, 16 to be conservative. Right now, in the time that Andromeda was not observable, we have 5 magnitudes decline into the observed luminosity in I-band. Actually, that is something that we are looking forward to confirm eventually, because as I said, the data set was really iffy in that respect, because if that turned out to be true, it is much faster decline than it would have been expected. And again, it is something very interesting in terms of observational characteristics of the event. Probably I should have given that earlier, but this is to give you an idea where the object is located in Andromeda, over all the directions, and we have M32 there. I guess that probably it is within some of the ground-based surveys, but I'm not sure if I don't know these surveys in details, and if the progenitor system will be easy to detect. And generally with that image, I'll just give a brief outline of the future work that we are planning. Of course, first thing for every astronomer is get more data. But the interesting part is actually that one thing that is particularly lacking for that particular transient are near-infrared observations. There is just one data point in JHK that was reported from some observatory in India. I don't remember exactly where it was located, but it was a relatively smaller facility. And for example, that could be something very nice to do for the science verification for CIRCE at the GTC once it is available for science. Something else that I've been going through the proceedings of the conference that was held here for V838 Monocerotis. Something that is missing generally for similar transients is mid-infrared spectra, for example. And again, here we have a unique capability, because right now Gran Telescopio Canarias has the only mid-infrared camera that is I would say available to the astronomical community, not only ground-based but also in the space. Okay, if we're talking about obtaining spectra, to clarify. Also, I think that monitoring the evolution of the optical spectra is really important to compare with the other events that were observed in that class, mostly with the transient that appeared in Monocerotis, obviously, because there we have the richest library of spectra available for similar event. And other things that I'm particularly interested in, now that we are really getting closer to pushing out the first official, how to say, paper on that, I want to sit down with the Spitzer archive and see if the progenitor system is identified on the Spitzer data. That basically is aided by the fact that at the end we got all the data together and did much more accurate astrometry that is going to be beneficial once you start searching into the archives. And this is generally the letter that we are going to be sending out shortly. Right now it is going through the final iterations with all the collaborators. And generally, as you could see, it is a pretty big collaboration covering different observatories and institutes in the US, Europe, Russia as well, and of course there are people here from GTC and respectively ISC as well into the collaboration. Unfortunately, and this is also has something related to ORM. People that were using the Liverpool telescope, it is really nice to have a robotic telescope at your disposal for that. They already published a paper on that object, but generally I would say that the two letters are complementing each other, because although they have much more homogeneous spectral data set, it's also lower resolution, and they could do the follow-up to a point before we actually stopped obtaining spectra. And also they have mostly photometry in the Sloan filters, which is, I would say, generally complementing the data set that we have really nicely. They get a little bit fainter maximum magnitude. I think that is just a way related just to the way they were working with the extinction estimates and all that. And with that, thank you very much for your attention. I hope that I didn't bore you too much.
So, Peter, I was wondering what's the expected magnitude of the progenitor? Because I'm thinking about whether we could. I don't have access to the pandas data, but I have been working with some of the data set, and they get several. They get about 3 magnitudes below the tip of the red giant branch, which would be in M31. So the tip of the red giant branch is an absolute I-band magnitude of. I have to get this right. Would it be 0 or -4? I don't know. Anyway, what's the expected magnitude of the progenitor? Would you expect?
Generally, one of the telegrams that got published during the hype around the object was dealing with estimates of the progenitor based on theoretical models and the observed magnitude at maximum light. So generally they were claiming that considering the magnitude of the event, it is expected that it is a merger of main sequence stars. So I would say that 3 magnitudes below the tip of the red giant branch is not going to be enough to...
Well, it depends on the mass of the main sequence star, but...
yeah, that is correct, but I would say...
Yeah,
if I remember correctly, it was between 5 or 7 solar masses, something like that. And
so you probably don't detect it. But
yeah,
it might be worth looking.
When I was looking at the HST images, you could see something there, but then we ran into the other problem that actually into the error circle that we had at the time, there were too many stars that were possible candidates.
Yeah, okay, so that's the crowding or whatever.
Yeah. It's, I would say, the luminosity of the progenitor is fairly low too.
Yeah, determining from the spectra you have, well, maybe it's not enough resolution, but to get the parameters, I mean the temperature, gravity, and everything.
Yeah, that would be possible, but I'm not sure how. No, that is one of the things, and also there is another thing that here we are talking about expanding photosphere, and it is not like a star into an equilibrium. So even if yes, yeah, And it would be really nice if we have a little bit higher resolution, but for a higher resolution, even with GTC, it would have been.
That's interesting because that's the follow-up in that way. You determine how all these parameters change.
Actually, there is something that we're planning to do in one of the things for the future work that I basically just forgot to mention. We got contacted by the group that is actually working with the auto detection system. And they said that they have about 2,400 data points of that object that they don't have the time or the ability to actually analyze. And they are willing to give us the entire photometry data set. Something that could be done basically with the data that we have and combining with that data set, generally derive rough spectral classes and roughly corresponding parameters based on the color evolution. And that is going to be interesting because right now with that data set we have much better temporal resolution compared to what we have with all the data that was acquired.
Any more? Then we should probably move on to the coffee break, but let's thank Peter again. Thank you.
Something that